Hello everyone, this is Usman Lone and I'm going to restart my calculus series. I know it's been a while since I've uploaded, but I think I'm going to do everything probably up until differential equations and multivariable calculus, and depending on how successful the series is, I'll see if it's worth continuing it. So I'm going to restart everything and start back from scratch, back at the first principles. So here we go. So lesson 1, what is differentiation? Well, it's this really useful thing in maths that's basically for working out gradients and the rates of changes of things. So let's say we have some function. This function could be f of x equals 2x squared. Now, this will probably look a little something like this. Though this should really be touching, so just improve that drawing a little better. So this is a function, and let's say we want to work out the gradient at this point. Well, what do we do if we don't know calculus? We would draw a tangent to this line, to this point. We would find some points on this tangent, and we do the change in y over the change in x, and this would give us our gradient. Simple enough. However, as you probably can see, there's some flaws in this method. This tangent has to be 100% accurate to give us an accurate gradient, and that can't always be guaranteed. Also, it seems kind of unmathematical to have to draw a tangent every time, and surely there must be some precise way to do it every time. And that's exactly what differentiation is. It's about finding the gradient of things like functions and finding the rates of changes of things, just so that we can find what happens to these functions a lot easier. So let's just take this graph, make it a little bigger, and see what happens. So when I drew my tangent, this point, it could be anything. So let's just call it x and f of x. That's the x value is x, the y value is f of x. Hope that makes sense. Now let's just pick a random point, any other point on this graph, and we give this point the name x plus h. Actually, I think probably makes a bit more sense to do it the other way around. So let me just call that x plus h, and this point x and f of x. So f of x is just some random point, and f of x plus h and x plus h, that's just another point that would distance h between the x values. Now you notice that if we draw a line between these, it's kind of like this tangent but different. The angle is quite different, the gradient is very different, it's a completely different line. However, what you'll notice is, as this h gets smaller and smaller, so I should probably draw the tangent here. So for this point here, this x and f of x, the tangent's going to look something like that. Now you'll notice that as this point h gets closer, the tangent between these gets more similar to this. Let's say we draw another point here. This tangent is also very similar. So, and more and more. So what you'll notice is, as this h value gets smaller and smaller, the gradient becomes more and more like that tangent. So as this h approaches 0, our tangent line gets closer to this line between x and x plus h. So how can we denote this? Well, if we have 2 points that are x and f of x and x plus h and f of x plus h, how do we find the gradient between them? Well, it's the change in y over the change in x. So the change in y would be f of x plus h minus f of x all over x plus h minus x. which equals f of x plus h minus f of x over h. And we want this h value to get as small as possible, because as we can see, the smaller that it gets, the closer that gradient becomes to the gradient of this tangent, which is the actual gradient. So we can do something called a limit. We can take the limit of h approaching 0 of this function. And what this means is this h will get extremely close to this 0, but it won't ever actually hit 0, because if it did, we'd be dividing by 0, and mathematicians don't like that. So this h becomes infinitesimally close to 0, and some weird stuff starts to happen. So let's just take this function that we started with, f of x equals 2x squared. Well, if I plug that in here, f of x equals 2x squared, then this thing, which is called the first principles, which is one of the most fundamental things in calculus, this formula will tell me that the derivative, or the gradient, at any point on this curve is equal to gradient of f of x is equal to 2x plus h squared minus 2x squared. So all I did was replace the x for x plus h, just how functions work, over h. And I forgot the most fundamental part, the most important part, limit h approaching 0. Math teachers get pretty angry if you forget that. So what will this give me if I simplify this out? That will equal 2x squared plus 2xh plus h squared minus 2x squared all over h, which equals 2xh plus h squared all over h. And then this simplifies to 2x plus h with this limit, in front of it, lim h approaching 0 of 2x plus h. And this is very useful because we're no longer dividing by 0, so we can just directly plug 0 into h, which equals 2x. So this is quite nice because this tells us I seem to have made a mistake somewhere. Sorry, yeah, this is meant to be a 4. Yeah, because 2 times 2. I can't do simple multiplication. Plus 2. Plus 2. Okay. Is that all good? Yeah, looks good. Okay, so this is very useful because this tells us that the gradient at any point on this curve is always going to equal 4x. So let's say I want the gradient at x equals 0. Well, just plug in 0 and I get 0, which makes sense because at x equals 0, the gradient here is 0, more like that. But if I want the gradient at x equals 100, let's plug in x equals 100 and I get 400. So when x equals 100, the gradient of this is 400. And so on. So as we can see, this is quite powerful, and we can basically do this for any function we want. Let's take, I don't know, 3x to the 7th power. Now I'm not going to do it because that would take a long time, but it would give us 21x to the power of 6. Now you may have wondered how I did that so quickly in my head, and that's what we're going to cover next lesson, something called the power rule for polynomials. So until then, adios.